So let me just say a few more words about ideals. I'm sure this is stuff that you know very well indeed. So I have I in A, an ideal. I can pass to the quotients A mod I. So there's a map there, A goes to A mod I. Then there are these two conditions. I is prime and I is maximal. So I'm sure everybody has seen these before in different contexts. Let me just remind you quickly what they are. I is prime means that 1 is not in P, and AB in P implies A in P or B in P. So maximal, I'm just telling you the definition. The definition is that 1A is not in M. It's not in M. And M is maximal in the sense that M in I in A. Oh, sorry. Okay, okay. So I'm defining what it means for an ideal to be maximal. It means I've got this ideal in A, and if I try to make, if J any other ideal, implies that I is J, or J is A. Right? So I'm deliberately avoiding the possibility that the ideal is the whole ring. Right? So we'll see why in just a second. Right? And so this is saying that I've in ordering ideals under inclusion, this I is as big as you can possibly get without getting to the whole ring. So if I've got anything which is strictly bigger than I, then necessarily it's equal to A. Right? So I mean, this is just a definition, and I'm sure that most of you have already seen it before and understand it perfectly well. So there's a little proposition saying that I is prime. P is I. P is prime if and only if A mod P is an integral domain So remember, I defined integral domain last time. I insisted here that 1 is not equal to 0 and no 0 divisors. Right, so 1 not equal to 0 is exactly this condition here. And no 0 divisors means if I have two elements in this quotient here which are not 0, so that means I have an element A which is not in P and B which is not in P, then the product is still not 0. I'm not allowed to have two non-zero elements multiplying to 0, and that's just basically repeating this question. And so Pm is maximal, an ideal M is maximal if and only if A mod M is a field. Right, so if M is maximal, it means that I've got M in A, and they're not equal. And if I have, if F is in A and not in M, then there's a bigger ideal there, MF, strictly bigger, and this has to be the whole of A. Right? And this means that you know, there exists an A in A such that there exists an A in A and you know, some element M in M such that M plus AF equals 1A. Okay, so I'm just, the only thing I'm doing here is I'm reading this definition of maximal. So M is an ideal, M is a maximal ideal. So I take some element F which is not in the maximal ideal, and I consider the ideal generated by M and F. Then, because M is maximal, and this guy here is a strictly bigger ideal, then necessarily M and F together generate the whole ring A, and that means that 1A, this element 1, is in the ring. Right? So now if we set M equals 0, then that's just saying that A is an inverse of F modulo M. Right? And that means that AM is a field. A mod M is a field. So, you know, you can see the reason for insisting on this here. So I'm talking about the Nullstellensatz, so Hilbert's Nullstellensatz. So here I've got a field, K is a field. I've got K of x1 up to xn. I've got an ideal I in K of x1 up to xn. An ideal. Right. So I'm saying there's this statement called, which is that if I is not equal to the ideal 1, so it's not, if I is not the whole ring here, then, and K is algebraically closed, then V of I is not empty. Right, so here is my AN, so it's sort of coordinate system there. And so I tried to define this V of I. V of I is a set of points P, so V of I is the P such that f of P equals 0 for all Pn, for all f in I. Right, so I want this to be the variety defined by the ideal I. So the locus of points defined by the vanishing of these polynomial equations. Right. So how are we going to prove this? So the proof is, the proof is sort of basically long and complicated. It's going to take me all of the first lecture to describe the proof and to try to, you know, patch together all the details of the proof. So how are we going to prove this? So there's this statement, intermediate statement, called the weak Nullstellensatz. Right, and that says that in the ring K of x1 up to xn, the maximal ideals are all of the form M equals xi minus ai. So let me write this out in full just once. x1 minus a1, x2 minus a2, xn minus an. Okay, for some for some P is A1 up to AN in AN. Okay. Okay. So this is maybe the first place where you really get a kind of close connection between commutative algebra on the one hand and geometry on the other hand. So this is saying the points of the space here. The points of the space here are the same thing as the maximal ideals of the ring. So points in geometry equals maximal ideals. And this is an algebra. Okay, so I will eventually get around to give a correct proof of this statement. Right. So first of all, notice that x1 minus a1, x2 minus a2, xn minus an. So this guy is called, let's call him MP, is a maximal ideal. Right? Because what's happening here is I can take k of x1 up to xn. So I think of these as polynomial functions on an. And I can evaluate them at p. So I'm taking f here to f at p. Right? So when I do this, each of the xi's maps to ai. So this is one of my indeterminates, one of the coordinate functions on Pn, and here I'm just taking his value at the point P. And then if I've got a polynomial here, I'm just evaluating a polynomial at these points, right? And the MP is the kernel. MP is just the kernel. So obviously these guys here map to 0, but conversely, if something maps to 0, if I've got a polynomial here that vanishes when I set all the xi's equal 0, then the polynomial f is in this ideal. So if f of p equals 0, then f is in MP. So this is like the remainder theorem. Right, you remember the remainder theorem says that f of a equals f of a. Oh, I don't mind. If f is a polynomial of one variable, if f is in k of x, then f of a equals 0 if and only if x minus a divides f. Right. And if you think about the proof of how you get this, then you'll get the same. You'll get this statement as well. So if I have a method here of evaluating polynomials at a point, then that gives me a maximal ideal. And conversely, if I have a maximal ideal and I know that the quotient is k, so if m in k of x1 up to xn is a maximal ideal, and I do k of x1 up to xn is k is divided by m. Is k is the rest. Sorry, you can't read that. If k of x1 up to xn divided by m is k, Right. This gives an interpretation of M as all functions that vanish at xi equals ai in K. Right, but so the whole issue here is to know that when I take this quotient here, I get a field K, so we want that K is little k. So this is the main point. This is the main reason why I have to spend half an hour discussing the proof. Okay, so I repeat. Suppose I've got a maximal ideal. Suppose I've got any maximal ideal of the polynomial ring k of x1 up to xn. I take the quotient k of x1 up to xn divided by that maximal ideal. I get some field k. At the moment we don't know what the field k is. Right? Then, the xi's map to some ai in k. So this is just x mod xi mod m. Right, and then of course xi minus ai, then this means that m is the ideal of all functions that vanish when I set xi equals ai. Right, but the problem is to know that the ai is in k, so that this ideal here is actually corresponds to a point P. Okay. Okay. So the main fact here, which I'm going to prove over a little time, the main fact is this: that if K is a field and K in a ring containing K, suppose that suppose I'm going to put in two conditions, and that's going to suppose that A is finitely generated as a ring over K. Right, and suppose also that A is a field. Then this implies that K in A is an algebraic extension. So actually also A to K is finite. But at the moment, the thing I'm looking for is this algebraic. So A is going to be a field. So suppose I've got K in A. This is a field extension. This is one field contained in a possibly bigger field. Suppose that this guy here is not just a field, but is also finitely generated as a ring over K. Right? Then actually this K in A is not just a ring extension, it's not just a field extension, but it's an algebraic field extension. Right? So in particular, if K is algebraically closed, then K equals A. Right, then there isn't any extension happening there at all. Okay, so this main fact, both in the textbook and in my lectures today, I'm going to, say that it's hard and defer it for a minute, defer it for a while. So let's believe this. So proof of the weak Nullstellensatz. So basically this is now already finished. So m in k of x1 up to xn, a maximal ideal. So make the quotient k equals k of x1 up to xn divided by m okay, then, and consider k into big K. Right, so I have k is contained in here, and so it maps down to this quotient. This is a field homomorphism, and it's not 0 because 1 here maps to 1 there. Right, so a homomorphism between fields is never, is always injective. Right, so it's just the definition of a field that 0 is not equal to 1. So 0 is not equal to 1 here, and that implies that 0 is not equal to 1 here. The field extension 0 goes to 0 and 1 goes to 1, and so the map must be injective. Okay, so this satisfies these two conditions. Of the main fact. Right, so I'm assuming here that this is the polynomial ring generated by x1 up to xn. So the quotient, everything in the quotient is still a polynomial in x1 up to xn. Right, and k is a field. The big K here is a field because m is a maximal ideal. Right, and therefore, K is algebraically closed. So that's just by the assumption in the so K is algebraically closed. That's also an assumption here. K is algebraically closed, therefore K equals K. Right, and this means that M, so there exists AI in K with Xi minus AI in M. Right, so the K here is appearing in two different contexts. It's the sub ring of this, and then it maps to the quotient K, which is little k. Right, so I take the value. I'm explaining something that's obvious. I take the xi here that map to AI in the quotients, and the quotient is little k, and so then this is a little a in k. Right, and then xi minus ai map to 0 in k. Right, I'm just explaining something that's already basically obvious. Yeah. So in other words, by doing this, so let me sort of try and stand back and repeat the argument. I've got a maximal ideal in the polynomial ring k of x1 up to xn. Right, I can pass to the quotient. So I have little k maps to polynomial ring here, maps to the quotient by this maximal ideal. Right, and so that gives me a k maps to k. Right, I have a little algebraic trick here, this main fact that I'm talking about. I haven't proved it yet, but I will prove it. So that says that when I have this, this is necessarily an algebraic extension of field. So the elements here are algebraic over K. Right? Also, K is algebraically closed, and so an algebraically closed field doesn't have any non-trivial extension field, so therefore K is K. Right? And then you think about where the xi's have to go to, and you figure out that this maximal ideal M contains one of the guys I already discussed, and so therefore is equal to one of the. Right, so the main fact implies the weak Nullstellensatz. Right. I want to say that also the weak Nullstellensatz implies that V of I is not empty. Right, in this statement here. So why is this? So I've got I, a ring, an ideal in K of x1 up to xn. I'm assuming not equal there. Right? So now I say, I pretend that I'm an algebraist, that I'm doing just algebra. Then, so I is an ideal. So it's contained in a maximal ideal. Okay, so you could, if you want to, some people would at this point say, well, Noetherian rings, we proved Noetherian rings. I can in any non-empty set of ideals, I can find a maximal one. So take all the ideals containing I. That's certainly non-empty because I itself is in there. Then take a slightly bigger ideal, slightly bigger ideal, slightly bigger ideal, but never allowing you to go to the whole ring. And so this is some set of ideals, non-empty, so it has a maximal element. The maximal element is then a maximal ideal. Okay, so you can do this just in terms of. On the other hand, you can do it also by Zorn's lemma or the axiom of choice if you want to. Right, every ideal is contained in a maximal ideal. So this actually uses Zorn's lemma or the axiom of choice, but I'm not interested in logic in in set theory or the axiom of choice. Okay, so if anybody wants me to explain this, I can do it, but it's sort of basically nothing to do with mathematics. It's just to do with set theory. Right? And so I've got I, and he's contained in a maximal ideal, and the weak Nullstellensatz says that the maximal ideal is of the form x1 minus a1 up to xn minus an, with the a1 up to an in P, in an over K. Right? And this is exactly what we want. So here there is this ideal. I started with an ideal, I assume it's non-trivial. I pass to a possibly slightly bigger ideal here. This ideal here consists of all the functions, all the polynomials that vanish at this point P. Right? And so this is saying that given the ideal I, there exists a point P so that all the functions I are contained in the ideals of functions that vanish at P. So this says that f at P is 0 for all P, for all f in I. Right? So this is the existence of the point P. So the thing I've proved here is the existence of a point P in V of I. Okay, so you know, at the moment we're doing foundational questions. I think as soon as you start doing algebraic geometry proper, you just sort of take this as obvious and you don't worry about it anymore. So you have to do the foundational things at some point. Okay, so the point I want you to remember is this one. Later on there's the full Nullstellensatz. So I stated it last time, the thing about radical of ideals. So the thing to remember is this, so I in k of x naught up to x1 up to xn not equal to 0 and k algebraically closed. This implies that v of I not empty. So I'm putting it in a box so that you remember it. There are lots of sort of details here that you have to. If you ever have to give this lecture yourselves, you'll need to remember it and so on. But basically, it's not all that. So I mean, this is also useful intermediate statement. Okay, so how am I going to discuss this main fact? So I have k in A. So this is finitely generated ring extension. And it's a field. I want to prove that then it's an algebraic extension field. So let me explain why it's true first and come to the proof afterwards. So suppose I take k, suppose it's not algebraic. So suppose this extension k to A is not algebraic. Then it means that, so if not algebraic, then there exists some t in A which is transcendental. And so this means when I do k of t, the field k of t, right? This is A is a field, so the polynomials in t are certainly in A, but also all the fractions are in A. Right? And so this as a ring, so this is a field extension. K of t is rational function field. Okay, so now let me write down k of t in there. So let's sort of imagine that we now have to write down ring generators for A. So, then I have to put in, so then A contains 1 over t, and 1 over t minus A, and 1 over t squared minus A, and so on. So the point I want to make here, the point I'm trying to make is that there are infinitely many possible denominators. Okay, so think about this polynomial ring k of t, k of square brackets t. So k of square brackets t has infinitely many primes. Right? So if you think of the argument why the ordinary ring of integers has infinitely many primes, it's basically the same argument. If I've got P1, P2, P3, P4, and so on, P up to Pn, I can take the product of all of those plus 1, and that's co-prime to all of the primes I have so far. Right? So when I want to make k of t inside A, well, you know, somehow or other I've got to put in at least one generator having each of these things here as a denominator. So if the field k is infinite, there are already infinitely many things of the form 1 over t minus a. Right? If it's a finite field, then there are infinitely many different polynomials here of different degrees. However, you know, it's just a basic fact that a polynomial ring has infinitely many prime ideals, and I have to put in one denominator for each of them, right? And that contradicts the fact that I have a finitely generated ring extension. Okay, so this is not a proof, it's just an explanation of why the result is true. I think it will be quite hard to make this into a proper proof. So the next thing I'm going to say is a sort of attempt, an idea to prove it that's wrong. So here I've got k, and I'm going up to k of, let's say, some elements. Let me call them, I don't want to use xi. So suppose I've got k of alpha 1, alpha 2, up to alpha n. I'm sorry, square brackets. Ring generators contained in A. Right, so A is a field, and I'm saying that under additional assumptions, if I have a field extension, if I have an extension of fields like this, then the alpha i's must be algebra. So I want to say that this implies that k of alpha 1, alpha 2, alpha n minus 1 is a field. So is this true? Right. So you know, the proof I'm going to give passes via this idea. It passes. It contains the idea that I'm going to you know, think about each of these elements one at a time, adding one at a time. So is it true? Is it true that you know, B contains in B of single element alpha, if this one is a field, that this necessarily implies that B is a field? So is this going to work? Well, I wouldn't be asking it if it were obviously true, so you should suspect that something's happening. So we'll see. This is sometimes okay. Okay, so it'll be especially when B is finitely generated over a field. Right, so I'm putting this argument up. This is wrong, this is false, but I'm putting it up because there are two useful things to get from it. Okay, so let's counterexample. And this counterexample will tell us what a local ring is at the same time. So let's think about Z contained in Q. So how do I get from Z to Q? So this is the field of fractions of Z. So I mean, of course you know the construction. This is the set of all n over m such that m is not equal to 0 and equivalence relation. Suppose I want to get Q as an algebra over Z, as a ring over Z. So what I'm going to do is, I might do this. I might do Z and put in 1 over n. And then maybe do 1 over n2. And so on. Right? So the obvious thing to do here is put in 1/2, and then 1/3, and then 1/5, and then 1/7, and then 1/11, and so on. Okay, so I hope you're seeing what I'm doing. An element in Q has got a denominator, right? The denominator is any number. It can have any prime factor in it to any power, right? So if I put in 1/2 here, so the ring Z of 1/2 is, I have got a half and a quarter and an eighth and so on. I've got all the powers of, I've got all the ring elements generated by 1/2. So if I put in all of these primes as denominators, then of course I get everything in Q. So what happens if I do this? Z of 1/2, 1/3, 1/5, 1 over P, and so on. So this is Q. Right? And so suppose I take one of these guys and say, right, you're not allowed him in Q. So this ring here is called Z localized at P. So this is the set of all rational numbers, n over m, such that m is not in, so n and m are in Z, and m is not in P. Okay, so here when I say Q, when we do rational numbers, you're allowed any denominator you like. Right? Here I'm saying, well, you're still allowed a lot of different denominators. The only thing, you're not allowed the denominator P. So I could say, for example, I'm interested in questions of divisibility by 5. I'm going to throw out everything else. So this is called the localization of Z at prime P. Right? And this is our first example of a local ring. So, you know, when you study Z, when you talk about prime numbers and so on, we're interested in factorization in Z. And factorization of Z involves all of the primes, all of the infinitely many primes. Right? And so in this ring, this ring here is still a unique factorization domain, but it has only one prime element. Right? I've just said, right, all the guys except for this prime P are invertible. Right? So we're going to need this idea of local ring later on in the course, and it's useful to give an example now, and it's also a counterexample to my proof. Okay? So if I do Z of P, and I just adjoin the one element 1 over P, then this is Q. This is a field, and this one is not a field. Okay, so the answer here is no. But it will be true if B is finitely generated over a field. So, you know, I'm telling you the thing that doesn't work first, because the thing that doesn't work is very, very similar, very closely related to something that does work. but then I need some more apparatus. So I need to say integral finite ring extensions. So the thing you're seeing here, in all of these examples, in all of the things I've said here, you know, this is just philosophy. This is what's happening behind the mathematics. So I'm saying that I'm trying to prove that, you know, this field extension here I've got an extension k to big A between two different fields, and I'm assuming it's finitely generated ring extension. So the thing that's happening here is this kind of divisibility. I'm putting in denominators. Here I'm telling you I need infinitely many denominators. Here I'm saying, well, you know, is it true that if I only need one denominator, that necessarily the thing was already a field? Okay, so I'm coming to this. These are basic ideas in commutative algebra. You know, unfortunately, we have to develop them. We can't. Ring extension. A to B is integral if every B in B satisfies a monic equation over A. Right? So this means B to the n plus A n minus 1, B to the n minus 1 plus B1 plus A1B plus A0 equals 0. Right? And the important thing here is that the coefficient here is 1. Right? So the coefficients AI are in A, and the 1 and the coefficient of B to the n, the highest coefficient, is equal to 1. Yeah, so this is monic. So remember, when you do field extensions in Galois theory, if I do k into k, field extension in Galois theory, if I've got some element b in k is algebraic over k, and this means the same thing. It means that b to the n plus a n minus 1 b n minus 1 plus right, where these coefficients here are in the smaller field. Right. However, here, you know, this condition an, we can set, if an is not 0, we can set it to 1, just because we're dealing with fields. Right, so this is just a parenthetic, just a remark. Right, so this is the same, this is almost the same as the definition of algebraic extension of fields in Galois theory, except that here I'm insisting we're working over a ring A. We're not necessarily able to divide out by this leading term, so I insist that when I have this algebraic relation for B over the smaller ring, that it has coefficient 1 there. So, you know, if you know algebraic number theory, for example, this is part of the definition of an algebraic integer in an algebraic number field. A ring of integers in an algebraic number field is defined exactly using this method. So, so what do I want? So finite. So this was integral, and now I'm going to tell you finite. So B is finite over A. Means that there exists a finite set, say B1 up to Bn, such that B is A times B1 plus A times B2 plus A times Bn. Right? So this is i.e. So this finiteness, i.e. finite, B is finite, finitely generated as a module over A. Right? So when I say finitely generated, I'm putting in these elements, I'm taking this ring here, I'm putting in these elements alpha I, and I'm allowed to use, for example, powers of the alpha I, or products of the alpha I. I'm allowed to, these elements here are ring generators, so I'm allowed to use all the ring operations on them. Right, when I'm doing this thing here, the BIs, I'm only allowed to do linear algebra on them. The BIs, I'm not allowed to take products of the BIs or powers of the BIs. I've got to take the BIs themselves, possibly multiplied by elements in A. Right? So this is a finite module, a finite algebra. Right? And now, there's this result, which is not completely true, but let me sort of state it as a thing to think about. Integral is the same thing as finite. Right, so this is not true. This is just a sort of way of thinking. So you use exactly the same trick when you do Galois theory. I've got a field extension. So one way is if B is integral. If B is integral, right, then I write down, then inside B I can write down 1 B squared, B cubed, and so on, V to the n minus 1. And then when I write down Bn, this is sum of AI, B to the I. Right? So in other words, if you've got an integral extension, and you think about how this element B appears, so if B appears now as a ring generator, I'm going to take all the successive powers of B, and when I get to the nth power, I get a relation, so I don't need Bn anymore. So this is saying that B is integral. This implies that A extended by B in B is finite. It's finite A algebra. Yes? So I'm just using in a completely stupid way the relation here. I'm using it to say whenever I see beta a higher power, I can replace it by linear combination of beta smaller power. Right? So that says something like integral and finitely generated implies finite. And there's another way round. So if finite implies integral. Right, and this is something which is not so easy. So, when you do field extensions, if you think about field extensions, so if I've got, so for fields, right, I've got 1 and b squared, b to the n minus 1. And so let's assume finite. So let's assume I've got k in k finite field extension, finite extension of fields. So this means that the big field K is a finite dimensional vector space over little k. So I start putting in these elements, 1, b squared, and so on. I'm thinking of b as in there. Right? And then, after a while, this is a finite dimensional vector space. So after a while, I get a linear dependence relation. Right? And then I get a linear dependence relation. Okay, and so therefore I get a relation saying b to the n equals sum of minus ai b to the n. Okay, so that's over a field. Right, now this argument doesn't, unfortunately, as it stands, does not work over a ring, because it gives me a relation, all right. It gives me a relation with a n, b, n there. But so what? It doesn't tell me anything at all about how to get a relation with 1 there. So this is proposition 3.12. Is it 2 in UAG? Right, so suppose that A in B is finite, then every B in B satisfies the monic equation then every B in B is integral over A. Okay, so I've been explaining to you how not to prove it. So this argument here just doesn't work. So this is one of these little tricks of commutative algebra, and you just have to use the fact that people have been studying commutative algebra for a century and know a lot about it. So the proof is determinantal trick. Okay, so B, let me take B to be sum of A, B, I equals 1 up to n. Right, and let me I don't want to use the same letter. Let me take every C in B as integral over A. So now consider C in B. Okay? And I want to think of multiplication by C. Right? So here I was saying I'm going to take this element B, I do 1, b squared and so on up to b to the n minus 1. And then when I get to b to the n, I've automatically got a relation. Right, so this works for fields, but it doesn't work for algebras. So instead of doing that, I'm going to take this element C, and I'm going to multiply C times each of these BIs. So C times BI. Right? Well, you know, this guy B is a ring. So C times BI, multiplication this is just multiplication in the ring. Right? And so I take BI and multiply by C, and I must get something. So let's call this gamma ij bj. So I said this is a determinantal trick. So I want to think of that equation as saying that gamma ij minus C times delta ij times whatever is it, BI is 0. So I'm looking at this, you know, the BIs so this is something that happens again and again in harder algebra. I've got some problem in algebra, and what we're doing is reducing it to linear algebra. So I'm assuming here that this B is made up of linear combinations of BI. With multiplications by elements in A, right? And I want to prove something about C. And so I do C times, I consider C as a method of multiplying inside B, right? So C times BI is this gamma ij times bj, right? And so in other words, I really want to think of this C as a matrix, which is the matrix gamma ij. So I apply it to a column vector, and I'm getting this product, the same as this matrix applied to product. So I can think of this as a matrix. Right, times all the vectors, all the bj equals 0. Right, and it follows that the determinant of this matrix is times all of the bj is 0. Right, so the thing I've got written out here is something in linear algebra. This is I'm thinking of the bj's as being, you can think of them if you want to as being a basis for the free module, some number of copies of A. Anyway, I mean, you know, this is, so anyway, it follows that determinants of sigma gamma ij minus C delta ij times bj equals 0 for all j. Right, and then this implies that this determinant sigma gamma ij minus C delta ij is 0 in B. And so this is a matrix now with minus C's down the diagonal. I'm sorry, minus C plus gamma ii. And then gamma ij here. When I take the determinant, all these gamma ij's are in A. Right, so this says c to the n plus lower order terms in C with coefficients in A. Is 0. Okay, so I'm not going to justify this. You can, you know, I don't know how you were taught linear algebra. And for that matter, I don't really know how I was taught linear algebra. But so this is, you know, you can think of this as coming from Cramer's rule for how to solve equations. Okay, so I needed this. So, you know, I mean, I'm not stating this formally. You can look at proposition 3.12 if you want to see the proper statement. But if you've got an integral extension, if you've got a ring extension which is integral, the way to use that is to say, let's take finitely many elements. The ring and the sub-ring generated by finitely many elements is finite. So that's integral implies finite. Of course, integral and finite. Maybe I should make a correct statement instead of. So proposition 3.12 says that's integral. So for A and B ring extension, integral plus finitely generated implies finite, and finite implies, well, all right, I can just write it for Univ. Okay, so the finite implies integral is the thing I've been saying is not trivial here. You have to know the trick to be able to do it. Okay, so what? So I've just rubbed out the main thing I was talking about, which is that is it true that K, what was it? A into, is it true that B into B of alpha, this one a field, implies B as a field. Right? So this is the thing I told you is not true. So no, in general, right, in the counterexample, because of this counterexample. But it's okay if alpha is integral. Over B. Okay, so this is a very, very trivial trick. You know, so this is, let me just say it, it's a proposition A in B, a ring extension, suppose that B is integral over A, right, so this is this thing, every element of B satisfies an algebraic dependence relation over A, which is polynomial and with leading coefficient 1, a monic relation, then B a field implies A is a field. Okay, and so, the arguments up to now have involved some non-trivial things. This thing is completely trivial. Right, so because if I take c in A, then c to the minus 1 is in B. Right? So, yeah, okay, I should take c not equal to 0. Right, so A going up to B is a certain ring extension, and we're assuming that B is a field. Right, so if I take an element in A, maybe I don't know how to invert him yet in A, but I certainly know how to invert him in B. So then, c to the minus 1 to the power of n plus a n minus 1, c to the power of n minus. So then there exists, so the important thing, this is still a monic relation. There exists a monic relation that is with coefficients ai in A. Right? And now just take this relation and take this and multiply by c to the n minus 1. That gives c to the minus 1 equals, and then it's minus a n minus 1 minus a n minus 2c to the power of 1, and then okay. So when I'm going to be involved in this, when I'm going to be involved in trying to prove this main fact, this thing I'm describing as a hard fact, then I've got some field extension, I've got some extension of fields, and it's finitely generated. And now I can say, I can take these guys one by one and say, and get rid of them and say that we go down to a field. And so anyway, this is the key to the proof of this main fact. So I'm sorry this seems to be going round and round in circles, each time involving stranger ideas from commutative algebra. The argument in the book is a little bit more relaxed, okay. So I'll deal with the homework at the beginning of the next session.